I will be discussing. Okay, in this session, I will be discussing how we visualize fluid flow and temperature fields in optimal pin fin arrays using optical techniques for laser-induced fluorescence, LIF, and particle image velocimetry, PIV. So basically, there's two main parts in this report. First, we optimize the pin fins, searching for the optimal designs, and then we experimentally tested the optimal designs with the PIV and LIF. Talking about the basics principle of PIV, this is an optical technique used to measure the velocity of fluid flow. First, we mix the fluid with tiny tracer particles, and the mixture is illuminated by a laser source. Then a high-speed camera is used to capture these illuminated particles movement at two different time intervals. And by analyzing the displacement of the particles, which is delta x within delta t, we can calculate the fluid velocity. So with PIV, we can observe the flow patterns of fluid. About LIF, this is also an optical technique that measures the fluid temperature. Unlike PIV, where we mix the fluid with tracer particles, in LIF, we mix the fluid with fluorescence dye. And this fluorescence dye will emit fluorescence signal when being excited by a laser source. And the intensity of the fluorescence signal is then captured by a high-speed camera to generate something called raw image right here. And finally, we transfer this raw image into the temperature image by a calibration curve. So in this work, we use PIV and LIF to observe the flow patterns and heat transport in the thermal flow system with pin fins. And pin fins simply is a extended material that protrudes from a base plate and to increase the surface area and flow mixing. And we see pin fin heat sink in cooling system in many electronic devices like servers, computers, or networking products. And these pin fin shapes can be like circular, square, or elliptical, etc. And these are very common and conventional shapes. And because its popularity, there are a great number of work have been done, both numerically and experimentally in the past to study the heat transfer performance of these fin shapes. So in order to experimentally understand the flow patterns and heat transport around these pin fins, researchers have used PIV and a technique called thermodynamic liquid crystal, TLC. I tried to find an example with LIF for pin fin, but it seems there's no work has been done with LIF and pin fin before. So one of the main drawbacks associated with traditional pin fins is the wake formation at the fin downstream. And this is because the flow is separated from the fin surface when moving past the fin and leaving a low pressure regions formed behind the fin. And in this wake region, the flow is irregular and has low velocity, and therefore reducing the heat transfer coefficient. And the poor heat transfer coefficient in the wake can be seen in the graph of TLC with low values of Nusselt number at the wake area compared to other regions. Now we know the standard pin fins are ineffective in heat transfer, and simply increase the size of fin may not enhance the thermal efficiency since the pressure drop also increase. However, people still use them because due to the limitation of conventional manufacturing methods like CNC or casting. And this is the biggest advantage of additive manufacturing to enable the fabrication of complex designs and a widespread adoption of additive manufacturing plays a key role to encourage engineers and scientists to search for more effective designs. So the most important question in this work is, will the optimal designs overcome the limitation of the standard beam fins, and how to experimentally explain this improvement by observing the flow patterns and heat distribution. So we optimize beam fin with two different approaches. The first approach is using genetic algorithm, and the second approach is using a joint solver. I first introduce genetic algorithm. Genetic algorithm is a gradient-free method for searching optimal designs. The first two steps is to generate the randomly initial designs or populations, and then these designs are evaluated by either CFD or machine learning to get physics quantities like temperature or pressure drop to calculate the thickness function F. And the designs with lower thickness function F are selected to go to further steps involved in natural revolutions like selection, mutation, crossover. And we're not going to go deeply into this internal loop of this process, but basically this process will help to improve the design even better. And the loop is repeated until the optimal design converge. And finally, we end up with optimal design look like a bowling pins right here. The second method is the adjoint method. And the first three steps are just like what we normally do when building numerical simulation model. First, creating initial design geometry, mesh generation, and then running CFD analysis. And after getting the physics quantities like temperature and pressure drop, calculate the thickness function J and the adjoint sensitivity. And finally, the designs of the design parameters are updated based on the guidance from the adjoint sensitivity to minimize the thickness function J. And the process is repeated until the optimal solution converge. After getting the optimal designs from genetic algorithm and adjoint method, we printed these optimal pin fin heatsinks with powder bed fusion technique. On the left, we have optimized pin fin and its perforated form when we added a hole on it. And on the right, we have another optimized fin from the adjoint solver. And the cylindrical fin is used as a benchmark design for comparison. And the heatsink and the pin fin heatsink are then integrated into the assembly module before being fixed into the experimental system. And this is the experimental system where the pin fin heatsink assembly module is placed in the system central. There's a laser source coming from the top of the channel, a high-speed camera on the side view to catch a fluorescence signal. Two RTD sensors are installed into the heatsink base plate to measure the base temperature. And then a pressure difference sensor is used for pressure drop measurement from the inlet to the outlet. For PIV and LIF, we kind of visualize the space between two consecutive fins in the channel central. So that the red region drawn right here is a region of interest. First, talk about the flow patterns from genetic algorithms designs. The top figure is optimized fin, and the bottom figure is the perforated fin. What we first noticed here is the wake regions behind the fin. And in bifurcated fin, this wake is disrupted as the bifurcated fin introduce high velocity flow pass through this wake. So it helps to reduce the size of the wake. And also in the in optimized fin, the fluid flow is pretty low between the fin space at the lower position. And this but in the bifurcated fin, high velocity is introduced into this space, and as we see on the video, this flow travels up to mix with cooler flow on the top position. So this increases the flow mixing between the different fluid regions, leading to better heat transfer coefficient. And we know the fluid temperature is strongly affected by flow patterns, and here is the fluid temperature we get from LIF for the genetic algorithm fin designs. And due to the stagnant flow at the wake, the fluid temperature is higher in the wake regions, and this is what we see from both fins. However, in the fluid temperature at the lower region, in the bifurcated fin is lower compared to the optimized fin. And this is thanks to the high velocity flow introduced into these regions by bifurcated fin, enhancing flow mixing, therefore cooling down the fluid. And we know cooler fluid will take heat from the fin better. Now talking about the flow patterns of the optimized fins from adjoint method. First thing we notice is a wake. The wake size is larger in circular fin, but in the optimized fin, this wake size is greatly reduced. And we know this is a good thing to promote heat transfer. And another distinct flow pattern is from the optimized fin is that it creates high velocity and chaotic flow into space between fins. As it increase the flow mixing and therefore increase heat transfer coefficient. Here we are plotting the heat transfer coefficient of different designs. On the left side, we have fin optimized by genetic algorithm. And on the right side, we have fin optimized by adjoint method. And it shows that the genetic algorithm optimized fin has 32% greater heat transfer coefficient compared to the cylindrical fin. And the bifurcated fins show even greater improvement with 44%. For the adjoint fin design, it shows up to 48% improvement in heat transfer coefficient compared to the cylindrical pin fins. So to summarize, optimization technique like genetic algorithm adjoint solvers deliver much better designs compared to the traditional designs what we have been using for the case. And thanks to the additive manufacturing, we are able to fabricate these highly complex designs which offer much better heat transfer coefficient while keeping the increase of pumping power at a minimized level. And the heat transfer improvement is mostly attributed to the flow patterns induced by the optimized designs, like reducing the wake size, increasing the flow velocity at critical areas, creating slower and more chaotic flow to improve the flow mixing. And these physics phenomena can be thoroughly observed by visualization technique called like PIV and LIF. Finally, before rounding up the report, I would like to say thanks to great support from our sponsor, NASA GPL and SURF program. Thank you, and any questions? Okay.